Welcome to my laundry room. So here I have a level that's hanging, and it's hanging from two rubber bands, one rubber band here and another rubber band here. So this is hanging, and you can see from the bubble in the middle, the level is, well, level. And then there's just a hammer hanging off the bottom of it for weight. So what am I going to do? In just a moment, I'm going to take this hair dryer and I'm going to heat up the rubber band on the right here. So this rubber band is going to get warmed up. And I want you to predict, knowing that this rubber band is made of a whole bunch of polymer chains that all sort of want to wiggle around and all that stuff. When I heat up this rubber band on the right, is the level going to tip this way with this rubber band contracting? Or is it going to sag this way with this rubber band expanding? Or is it going to stay the same? Is heat or temperature not really going to have any appreciable effect? So take a moment now, pause and ponder. What do you think will happen? All right, now prepare your ears. I'm going to turn on the hairdryer. And I'm heating up the one on the right. And as I'm heating up this one on the right, So I heated up this one on the right. What do you see happen? Well, the bubble of the level went to this side here. So that means that this rubber band must have contracted as I heat it. And now I'm going to take a moment and I'm going to blow on the rubber band. Cool it off a little bit. And once it cools back down, you can see it returns to, pretty much the same level that it was before. So when I heated up this rubber band, it contracted, lifting up this side of the level, and then when it cooled back down, it returned to its original position. What's going on? Well, we'll learn in today's lecture. Welcome to Biomaterials. What are we going to talk about today? Well, today we're going to talk about a couple of things. Eventually we'll answer the question regarding that live demo that I showed at the beginning with the maybe intuitive, maybe counterintuitive result of the heated rubber band contracting. But today we're going to center our discussion on where does from a molecular standpoint, where does modulus of elasticity come from? So modulus of elasticity, and basically a sort of molecular viewpoint. And if we have this sort of molecular viewpoint of modulus of elasticity, it turns out that it's different for different classes of materials. So basically what gives rise to modulus of elasticity in metals and ceramics is actually a little bit different from what gives rise to modulus of elasticity in polymers. So we'll need to kind of consider those two separately. I'll take the somewhat simpler of the two first. We'll look at metals and ceramics. And basically what gives rise to modulus of elasticity in metals and ceramics basically has to do with the energy in bonds, in atomic bonds between atoms. So that's basically the energy in bonds between atoms, and changes in the energy in bonds between atoms as they're distorted is basically what gives rise to modulus of elasticity, i.e. stiffness, for metals and ceramics. It's a slightly different story for polymers. What gives rise to modulus of elasticity in polymers is actually an effect of entropy and chain configurations. And I'll essentially have some ways to sort of consider and describe and think about that, and think about why changing the configurations of chains sort of gives rise to an apparent stiffness in polymers. But before we get to that, let's talk about this first one. So if you zoom way in for metals and ceramics, if you zoom in to the atomic level, you often, not always, but almost always see some sort of regular structure or arrangement in these materials. So there's a regular structure, and we call this regular structure the crystal lattice. So if we have a crystal lattice, you basically have this very regular structure of atoms within that. And if we sort of focus on what's going on with ceramics, ceramics are often these are often oxides. Well, I guess, oxides aren't the only ceramics out there, but one example are oxides. So one example of a ceramic is an oxide. So let's, for example, take the oxide calcium. Let's look at calcium oxide. So calcium, if you remember, calcium typically takes on a 2+ charge. It's in the second column of the periodic table. Oxygen typically takes a -2 charge when it's combined. So if we look at a ceramic, a calcium oxide ceramic, there's sort of an equal number of calcium and oxygen atoms, and nearby every calcium, the calcium takes on a +2 charge. The calcium wants to be surrounded by oxygens, and all of the oxygens with their -2 charge want to be surrounded by calcium. So if we do a little bit of color coding here, let's have our calciums be red, and let's have our oxygens be blue. If we imagine there's, let's say, a calcium atom in some structure here, all of the adjacent atoms are going to want to be oxygens, and then around every oxygen, the adjacent atoms are going to want to be calcium. And then you can imagine, if each of the dots here that I'm drawing is an atom, this basically, repeats and repeats and repeats and repeats, all the way to infinity. And in fact, if you zoom all the way out, this atomic structure of the crystals actually gives rise to those like cool geometric patterns that you see in lots of rocks. So there are some crystals that you can like mine, and this atomic structure basically is so regular that it gives rise to sort of macroscopic regularity in the crystals. But anyway, I digress. What we care about today is what's going on at the atomic level. So now let's start off with a little pause and ponder question. So first, pause and ponder. Why does it require force to pull the atoms farther apart? Right, so if I wanted to take this structure here, and I wanted to take the ceramic and stretch it out, and in a sense, right, I'm applying normal strain, right? So it's essentially basically, why does it require force in order to impose some normal strain, but basically taking these atoms and kind of stretching them out and making the space between each one larger? So why does it require force to pull them apart? Well, it requires force to pull them apart because of the opposite charge of the calcium and oxygen. So opposite charges attract.
opposite charges attract. So in a sense, this oxygen right here tugs on the calcium, and this calcium here tugs on the oxygen, and they're sort of pulling each other together. So and you can imagine this basically does the same thing. Its neighbor basically pulls in. So all of these atoms, due to the opposite charges, want to get closer and closer and closer and closer, right? So in a sense, I'm basically taking, if I had a lattice that was spaced too widely, they're all sort of pulling on each other to get closer and closer and closer and closer, such that as this bonding occurs, that lattice kind of shrinks down and down and down and down. But you might ask, hey, wait a second, if all of these oppositely charged oxygens and calciums are pulling on each other to get closer and closer and closer, what stops it? What stops contraction? Right? If they're attracted to each other, why don't they just keep going and keep going and keep going? Well, hopefully you've had a chance to pause and ponder. If you dust off the high school chemistry, you remember that the outer electron orbitals are basically, and the nuclei are sort of what govern their charges and their attraction to one another. But the reason that they stop contracting is, can be from a couple reasons. One is the inner electron orbitals start to overlap. And repel. So, yes, this calcium is +2 charge. Yes, this oxygen is -2 charge, and they start to attract to one another. But if we think of these inner electron orbitals, if I sort of highlight them in pink, each of them sort of has a cloud of electrons around one another. And, those clouds don't really overlap too much initially, but once you get those clouds too close to one another, those electrons can't sort of occupy the same space. So that's one mechanism that basically stops those from just collapsing, into oblivion upon one another. There are some potentially other factors at play, but this is one that sort of conceptually you can think about that basically stops them from contracting. So what does that mean? So these two ideas together basically means that there's a sort of a happy medium where they're attracted, where they're sort of close enough to one another to satisfy the attraction of the opposite charges, but not so close that we have appreciable repulsion, due to inner electron orbitals overlapping or sort of other quantum mechanics-y sort of effects. And what does that mean? That basically means there's an equilibrium. There's sort of an equilibrium distance between the two atoms, and let's equilibrium distance, where essentially the attraction and repulsion are balanced, and we could call this, let's call this distance delta naught. So you can basically imagine that each of the atoms in the crystal lattice are sort of have this equilibrium distance delta naught apart from one another. And if you wanted to, you could sort of think about perturbations of this crystal lattice, and you could imagine like the sort of energy, the stored energy in the lattice about this equilibrium position delta naught. And you can basically imagine that if I tried to make the as a function of spacing, and basically if I tried to make these atoms too closer together, the energy would go up, right? So basically it takes energy to push these closer together due to this effect, but it also takes energy to move them farther apart. So I get this, so I get kind of this effect right here. So, if I look at stored energy as a function of spacing, it kind of, the energy sort of, the system occupies this sort of position of minimum energy by having this default lattice spacing delta. And if we want to think about things in terms of force, well, energy, energy sort of has units of force times distance. So then, so force is related essentially to the slope. The slope of this curve is essentially related to the force required to deform. So if you wanted to plot, force, or if you wanted to think of it, stress, it would look something like this, around this sort of position delta naught here. If I wanted to make it closer together, that force sort of becomes repulsive. If I want to pull them farther apart, that force becomes attractive. So force versus distance looks like this. So basically, like, if I pull them apart, they get attracted together. If I try to squish them together, they get repelled apart. So in a sense, they're always there's a force that's kind of always restoring this system to the equilibrium. And of course, if we think about force versus displacement, this is something that's getting awfully similar to sort of a stress strain curve, right? So in a sense, in the stress strain curves, and this position of delta naught, you can think of this as basically where we would set our strain equals 0. This is basically where we would set our strain equals 0 point, and we would essentially create a stress strain curve that basically starts at this point here. So basically this is what's governing the stress strain curve. And you can imagine different types of materials have different chemistries. So basically different chemistries are basically lead to a slightly different equilibrium position, but also potentially lead to steeper or less steep sort of energy bowls. So, different chemistries, you might have some chemistries that they like their equilibrium position and it takes a lot of energy to contract them and a lot of energy to expand them. And that would sort of lead to a very steep energy bowl right here, and it would lead to a steeper stress strain curve. Or alternatively, you could have a system that these atoms don't require quite as much energy to push together or to pull apart, and that would kind of have a much shallower bowl right here, and that would sort of lead to a shallower stress strain curve right here. So basically all of these have a different modulus of elasticity, and that's basically due to this sort of energy landscape between atoms. So that's basically what's going on. So this sort of explains why it's difficult, why it's more or less difficult to push together atoms in calcium oxide, for example, compared to magnesium oxide, or potassium nitrate, or sort of any of these other crystals. So this is the sort of rationale for what's going on in ceramics. Metals, you might say, hey, wait a second, why do metals have this? Why do metals have any attraction at all, right? Why are two metal atoms attracted to one another to pull them close together, but also repelled from one another to not make them completely overlap? Metals are a slightly different story from ceramics. We don't necessarily have this ionic attraction here, but basically two metal ions kind of want to share their outer electrons in these sort of metallic bonds. And for metals, metallic bonds kind of replace this first effect. So metals are sort of similar to ceramics in that they're attracted to one another, and they're sort of attracted to one another. That creates a lattice structure. but instead of ionic attraction, we get sort of a metallic bond, i.e. metallic electron sharing. And that can kind of create some attraction between two. That basically ends up with a similar effect phenomenologically. So this is the rationale for why. So this is basically on an atomic level why we have a modulus of elasticity. And if we think about modulus of elasticity, we're basically deforming. We're making atoms spaced farther apart or closer together, and to stretch them or contract them basically requires an energy input that we can sort of translate to a force versus displacement as well. So this is basically where things come about from an atomic level in terms of modulus of elasticity. So, thus concludes our discussion of this. Now let's talk a little bit about polymers. So if you think about polymers, so polymers and modulus of elasticity, which again we abbreviate typically as E for the letter of modulus of elasticity. So polymers are usually much less stiff than metals. So the modulus of elasticity of polymers is typically orders of magnitude below that of metals or ceramics. And typically when we have a polymer, we're not deforming the space between atoms themselves, but we're rather rearranging how chains are formed. So so you should be aware that polymers don't necessarily have this regular structure that atoms do in general. So polymers are basically composed of chains. And to deform a polymer, to stretch it out, i.e. to take the rubber band, to take this rubber band and stretching it out, so polymers are made of chains. I'm usually not stretching the space between atoms themselves, not stretching atomic bonds, but rather twisting and untangling chains. So what do I mean? If you were to zoom in to what's happening at the atomic level in this rubber band, what you would probably see, is a bunch of atoms, and basically the polymer chains take this kind of random sort of configuration here. So every vertex is an atom, and every line that I draw here is a covalent bond. And if you remember, single carbon-carbon bonds can rotate. So basically around these hinge points here, single bonded things, right? These single bonds here can rotate. So basically I can pivot around a carbon-carbon bond. So pivot permitted. And it doesn't, and it takes almost no energy to pivot these bonds. So minimal energy. So it takes minimal energy to sort of pivot these bonds, but it would take a sizable amount of energy to actually stretch out to make these bonds much longer or shorter. So you can imagine if I had a polymer chain, and let's say I had a plate here and a plate here and a polymer and a polymer chain between them, I don't actually need to stretch out. I don't need to stretch out these bonds too much in order to take that, in order to lengthen my sample of polymer right here. I can achieve lengthening by untangling, by having all of these bonds sort of twist in such a way as to straighten out the chain much more easily than actually stretching the bonds. So if I apply force, so I apply tension, and I untangle rather than lengthen bond. To extend the sample. So what does that look like? You know, that looks like that might look like this if I sort of stretched it out all the way. But then that leads us to the question, when I let go, so take a moment now, pause and ponder. When I let go, why does it return to this state, to contracted or tangled state? Well, it turns out that it has to do with heat and entropy. So the answer is heat and entropy. So the way I've drawn these polymer chains here is just sort of chilling, not really moving. But if you were to zoom in and take not just a snapshot, but a video of all of these things, if you zoom in on the atomic level, everything is jiggling around. They're not just these static things here. Unless you're at absolute zero, nothing is precisely still. Everything is wiggling around due to thermal energy. And basically this wiggling, right, if all of these things, if this guy wants to wiggle this way and this way and this way, and these guys want to wiggle this way and this way and this way, all at random times, this side-to-side wiggling is actually what sort of pulls us back in. So to illustrate that, I have a bunch of rope, right? This is just normal rope here. And if I jiggle this rope due to thermal energy, you can see, originally it was all I all sort of lined it up, imagined it was stretched out here. And if I jiggle this rope due to thermal energy, jiggle it all around, all side to side here, originally these edges were outside of the field of view, but after I jiggled it, it pulled itself back together. So what does it mean? It basically means that the heat contained within this polymer is sort of always drawing it back to this jiggled state. So what does it mean? It basically the conclusion here is heat jiggles us back to a random state. So if you imagine here, I've stretched it all out. If I take chains and stretch them all out perfectly, there's basically no randomness in a chain that's sort of pulley laid out, right? Like this is fully ordered, right? It's one line, and then the next one, and then the next one, and then the next one. There's basically no randomness here. So this is no randomness. The heat, if we have a system with no randomness, right? It's like cleaning your room. It takes a lot of work to clean your room, but it's easy to just let it get messy again. Basically, entropy drives us back to this state. And in a sense, randomness is basically related to how many possible configurations a polymer chain can have. Here, there's essentially only one possible configuration. And that basically means low entropy. But here, there are many possible configurations. Right? I drew one of them right here, but I could have just as easily have drawn, this one, or this one, or this one, right? There are tons and tons of possible configurations that have the same total length and get me from this point to this point if I allow those points to be closer together and allow it to sort of take this circuitous route. So what does it mean? Nature, if I sort of anthropomorphize it, nature abhors these low entropy configurations and instead wants to sort of pull things back to this high entropy situation. So in a sense, it takes energy to take something, just in the same way that it takes effort to clean your messy room. It takes an input of free energy to take something from a high entropy state to a low entropy state. So take a moment now, pause and ponder. What about compression? Right? Does compression? What about compression of polymers? So take a moment now, pause and ponder. How might entropy change with compression of polymers? How does that relate to the force on the sample and things like that? Well, compression, it's kind of the same story. If I had, let's say my original configuration between these plates right here, and I took these plates and then squashed them, I've now limited, I've limited the states I've limited that polymer. Right? That polymer used to be super random, but if I take it and squish it together, now I've created order by squishing. So it takes compressive force to push it together. It takes tensile force to pull it apart. And that's basically because there's entropy reduction in both circumstances. And it turns out that that you can, actually from nearly a theoretical standpoint, all this that's beyond the precise mathematical details are beyond the scope of what we can do in this class. But this allows a sort of near first principles prediction of modulus of elasticity from entropy standpoint. So there we go here. So but usually we don't use this, or you can just look up entropy, or sorry, look up the modulus of elasticity for your polymer of interest. Now, finally, you might be thinking about that demo that we did where we had the rubber bands and the level that was hanging. What was going on with that live demo? Well, if gravity's pointing this way, originally I had this thing, I had the clamps or whatever, and I had these two rubber bands hanging, and if you can imagine, the weight of the level. So here's the level, and I'm exaggerating the rubber bands here. the weight of the level was basically pulling these rubber bands a little bit. The weight of the level and the hammer was pulling them a little bit, so they were kind of aligned. You know, the weight was aligning some of the polymer chains such that they were not totally purely vertical, but mostly vertical, right? Sort of similar to what I did here. And, you know, now they were achieving kind of an equilibrium between how much entropy they had and how much force was on them. But when I heated this one, heat basically means they want, I'm going to anthropomorphize them a little bit, they want to be more disordered. Right? So when you add heat to something, it wants to be more disordered. It basically means more jiggling. More jiggling from an atomic standpoint. Right? I'm wiggling, you know, on the right side, I'm jiggling these ones a lot more than on the left side. So on the left side, they're kind of straightened out like this. On the right side, I'm jiggling them a lot more. And when I jiggle them, you know, that kind of just by random motion pulls the ends back together. So that basically means that after this heat was applied, you know, this one stays the way it was with polymer chains mostly aligned, and the level tipped up like this one because these polymer chains needed to kind of expand out to the sides a little bit to be more random. And that expansion out the sides basically caused contraction along its axis. And that basically made the bubble, you know, that made the bubble come up to this side, where initially the bubble was in the middle. So, thus concludes our discussion of the connection between modulus of elasticity for metals and ceramics and polymers, and how they're different to one another but also related. Thank you very much for watching, and good luck with your study of biomaterials.